Welcome to a mind-bending journey through time, from the fiery birth of our sun 4.6 billion years ago to its far-off fate as a cold, dark remnant drifting through space. Buckle up as we unravel every phase of our star's life, its stable middle age on the main sequence, its dramatic transformation into a red giant, the spectacular Helium Flash, the emergence of a planetary nebula, its quiet twilight as a white dwarf, and its ultimate cooling into a theoretical black dwarf. Along the way, we'll learn what happens to Earth and the other planets. Compare our sun to distant stellar exemplars like Betelgeuse and the Ring Nebula, and use everyday analogies to make these cosmic processes crystal clear. Ready for an epic ride through billions upon billions of years in just a few minutes? Let's get started! The sun's fiery birth in a molecular cloud around. 4.6 billion years ago, a dense pocket within a vast molecular cloud of hydrogen, helium, and interstellar dust began to contract under its own gravity. As the material spiraled inward, the central temperature and pressure skyrocketed, igniting the first nuclear fusion reactions. In a flash of heat and light, our protostar was born, the nascent sun. Everyday analogy. Picture rubbing two sticks of wood together so vigorously that they spark. That spark bursts into flame. Similarly, in the stellar womb, hydrogen nuclei ignited into a self-sustaining fusion fire. Astronomical example. Today's Orion Nebula shows us dozens of such protostars in the making, still cocooned within their dusty nurseries. The Golden Era, the main sequence. Stage 1's fusion became self-sustaining. The Sun entered the main sequence, a period of remarkable stability that lasts about 10 billion years. Here, hydrogen in the core fuses into helium, producing the energy that bathes our solar system in light and warmth. Sun today, we are about halfway through this phase. The photosphere glows at roughly 5,780 K, emitting some 3.8 x 1026 watts, enough to power countless civilizations. Impact on Earth. This steadiness has allowed liquid water to persist, enabling life to flourish. Analogy. Think of a high-quality LED bulb plugged into a stable power supply. It shines evenly for years without flickering or dimming. The slow burn. Hydrogen depletion and warming Earth over time. The sun's core hydrogen supply dwindles. Fusion shifts to shells outside the core, and the core contracts while the outer layers expand. As a result, the sun's luminosity increases by about 10% every billion years. In 1 billion years, a 10% brighter sun will significantly raise Earth's temperatures. Oceans may begin to evaporate. In 2-3 billion years, increased water vapor may lead to a runaway greenhouse effect, making photosynthesis nearly impossible. In approximately 4 billion years, Earth's surface could become uninhabitable long before the sun enters its final act. Analogy. Like a car engine revving higher without additional fuel, the sun's RPM rises, heating the planets from within. Ballooning to a red giant in about 5 billion years, core hydrogen fusion ends. The core collapses under gravity, heating up dramatically, while hydrogen fusion ignites in a surrounding shell. The outer envelope of the star inflates to form a red giant. Swelling dimensions. The sun's diameter will expand up to 100 times, potentially engulfing Mercury, Venus, and maybe even Earth. Cooling surface. The photosphere cools to about 3,000–4,000 K, casting a deep reddish glow across space. Real example. The bright red giant Betelgeuse in Orion hints at our own sun's future look, though Betelgeuse is far more massive. Analogy. Envision an overinflated balloon that swells to envelop everything nearby, its color dimming as it expands. The Helium Flash, a stellar second wind. As the core heats to around 100 million K, helium fusion into carbon and oxygen suddenly ignites in a dramatic event known as the Helium Flash. Though hidden beneath thousands of kilometers of stellar gas, the flash profoundly changes the star's structure. Consequence: the star readjusts, its outer layers contract slightly, and a stable phase of helium fusion begins in the core. Analogy: similar to a pressure cooker's safety valve releasing with a sudden hiss, then settling into a gentler simmer. Asymptotic giant branch and planetary nebula. Formation after helium in the core is exhausted, the sun swells again into an asymptotic giant branch, AGB star. Pulsations and strong stellar winds strip away the outer layers, creating a dazzling planetary nebula. Famous examples: the Ring Nebula, M57, And the Helix Nebula showcase the layered shells of gas cast off by dying stars like our future sun. Timescale: a few tens of thousands of years, a brief cosmic moment before the brilliant nebula fades. Analogy: imagine peeling an onion one layer at a time, each peel drifting off into the wind, revealing the core. Birth of the White Dwarf: when the outer layers are finally shed, the hot, dense core remains as a white dwarf, roughly Earth-sized, yet containing nearly the sun's full mass. Surface temperature starts around 100,000 K, slowly cooling over billions of years. Physics: electron degeneracy pressure prevents further collapse. Matter is packed so densely that electrons resist compression. Analogy: like a red-hot steel ball that retains its glow long after the furnace shuts down. Cooling to a black dwarf over truly astronomical timescales, trillions of years, a white dwarf radiates away its residual heat and dims to become a black dwarf, a cold, dark stellar remnant. Current universe: too young to host any black dwarfs yet, they remain purely theoretical. Analogy: think of glowing embers in a fireplace that eventually cool down to room temperature, leaving behind cold ash. The fate of Earth and its neighbors: during the red giant phase, Earth's surface will overheat and oceans boil away. Ultimately, our planet may be engulfed or left as a charred cinder. Inner planets, Mercury and Venus, almost certainly vanish. Earth probably follows. Outer planets: Mars might survive in a charred, barren state. Gas giants like Jupiter and Saturn will lose most of their atmospheres but keep their cores. Second-generation worlds. Some material in the Planetary Nebula may gather into tiny, rocky worlds orbiting the White Dwarf, our solar system's children of the second generation. Learning from other stars. Cosmic case studies. Astronomers study other stars at each phase to forecast the sun's evolution. Betelgeuse and Aldebaran offer insight into the red giant stage. Mira variables illustrate intense pulsations and mass loss on the AGB. Sirius B, a nearby white dwarf companion showing the fate of a sun-like star's core. By comparing observations of these objects, scientists refine models of stellar aging and death. That was our sweeping tour through the life and eventual death of the sun, from its calm middle age to a bloated red giant, through the magic of the Helium Flash, into a brilliant planetary nebula, the glowing white dwarf finale, and the silent drift of the Black Dwarf. Along the way, Earth faces an uncertain future, and new worlds may emerge from the ashes. If this cosmic saga fascinated you, hit like, subscribe for more stellar stories, and share with friends. Drop a comment below. Which phase of the sun's life did you find most mind-blowing? What stellar mysteries should we tackle next? Until our next space adventure, clear skies and safe travels.